In this video, we are going to be looking at combining power series. So if you have two power series and they have the same interval of convergence, it just so happens that you can combine them through addition, subtraction, multiplication, and you can raise a power series to a power. And so this particular part of this definition talks about how to add or subtract power series. If you have a power series, c sub n, x sub n, that converges to the function f, and you have another power series, d sub n, x sub n, that converges to the power series g, then adding the two power series or subtracting the two power series is a matter of adding or subtracting f and g. It seems simple, but this is a very tedious process. Likewise, part 2 here talks about multiplying power series. So multiplying two power series is a matter of multiplying b sub x sub m times f of x sub m, f of x, and raising to a power. So we're going to go through and do an example of each of these. So the first one, we have the function f of x is equal to the power series 2 to the n over n factorial x to the n. And the function g of x is equal to the power series of negative 1 to the n, 2 to the n over n factorial x to the n. And what we want to find is 1/2 the sum of f of x plus g of x. So to do that, what we have to do is we have to begin by listing out some of the terms, because we don't actually know what f of x is. We don't actually know what g of x is. So let's expand out some of the terms. So that's what I did here with f of x. Okay. And what I like to do sometimes is write my n numbers up above. N equals 0, n equals 1, 2, 3, 4, kind of like making a little table here. And so n is equal to 0. We end up with 1 for 2 to the n over n factorial times x to the n. And then 2x, 4x squared over 2 factorial, etc., etc. Now, one thing that you're going to want to get in the habit of doing is leaving these in terms of factorials. In other words, don't write 3 factorial as 3 times 2 or 6. Don't write 4 factorial as 4 times 3 times 2, which would be, 24. Leave them in terms of factorials. That's going to make it easier to simplify sometimes. All right, then the second power series, this one, I expanded out the first few terms from n equals 0 to n equals 4 and ended up with this expansion. Now what we want to do is we simply want to combine. We want to add these two power series together. So that's what I'm doing down here. That's what this big line is here. This is my line where I'm adding. So let's get rid of that. So 1 plus 1 is 2. 2x minus 2x is 0. 4x squared 2 factorial over 4x squared 2 factorial is 8x squared over 2 factorial. And then we get 0 and 32x to the 4th over 4 factorial. Now, every other term is 0, and that's because of this negative 1 to the n. So when we actually write out the terms of the series, we can omit the zeros. Also, don't forget that we're multiplying all of this by 1/2. That's crucial in this problem working out. So 1/2 times 2 is 1, 1/2 times the 8x squared is 4x squared, etc. So we end up with this expansion, the first 3 terms of the expansion. Now with this new expansion, this is n equals 0, n equals 1, n equals 2. And so what we need to do is we need to come up with the general formula for this power series. And so sometimes it's easier to skip the first term, which is just a 1. And you know that's usually going to come about when n is equal to 0. So when n is equal to 1, so here we have 2 factorial in the denominator, 4 factorial in the denominator. Now, because every other term zeroed out, we basically are left with just even terms. The factorials are even, the powers are even. Now, it might look like this would be n equals 2, this would be n equals 4, but actually this is n equals 1, n equals 2, and n equals 0. And so you can verify that this little formula that I've written here will actually work for this. Again, just like we learned back when we were working with sequences in series, you just have to play with these a little bit. But in general, if you see that you are working with just even terms, everything is even, x squared, 2 factorial, x fourth, 4 factorial. The next term looks like it would probably be 64x to the 6th over 6 factorial. We could go through and try to verify that. When all the terms are even, then look at having a 2n as a factor. 2n factorial, 2n to the power, because that usually will work. If it's odd, it'll be 2n plus or minus 1, because you can always guarantee an even number if you multiply it by 2. So if n is equal to 1 times 2 is 2. N is equal to 2 times 2 is 4. N equals 3 times 2 is 6. So it always ends up being even. All right, and that is our answer to this problem right here. Final answer is that. That is the power series. So it says find the power series that represents that sum. And so that would be the sum. That's what combining power series is all about. Next up, oh, this is a fun one. This one everybody's going to love. Because before we can do anything, we have to do a partial fraction decomposition. So this is a good review for decomposing a fraction into its component parts. And so we start by creating 2 fractions. We have two linear factors in the denominator, so we put 1 linear factor in each of the denominators. And because the factors in the denominator are linear, we put a constant in the numerator. And then we multiply both sides by the least common denominator to get this. And the least common denominator will always be this denominator, remember. Then we combine the terms, so we're multiplying through ax times 7, b times x minus 9, and we get this term right here. Check the algebra. And then we equate coefficients. That's the way that I like to do it. There's a couple different techniques at this point. And so I take the x terms. So x is equal to ax plus bx, or 1 is equal to a plus b. And then we have, let's do say green. So then we have 39 is equal to 7a minus 7b, which I put over here. And then I need to solve the system of equations. I have 1 is equal to a plus b, and 39 is equal to 7a minus 9b. So I multiply this by 9 and get this, so that I can eliminate the b's by adding the two equations together, getting 48 equals 16a, or a equals 3. Once you have that, of course, you can go back to 1 is equal to a plus b, which I did over here, substituting in the a equals 3 and getting b equals negative 2. All of that is just to decompose the fractions. All right, so instead of writing 3 over x minus 9 plus negative 2 over x plus 7, I would prefer to write it as minus 2 over x plus 7. Now, I may change that as I'm going through this problem, but right now I'm just going to write it as minus a positive 2 over x plus 7. Next step up, once we have that, what we want to do is we want to write each of these as the sum of a geometric series. We want to write it as a sum of a geometric series. So this is what we did in the last section. The general form of a sum of a geometric series is a sub 1 over 1 minus r, remember. So, first of all, I need to have the r value. Second, the 1 comes first, so I have to switch these two terms around. So I make it 9 minus x. In doing that, I have to factor out a negative. I put that negative in the numerator. Then I want a 1 here, right there. So I have to factor out the 9. And so we did this in the previous section. Factor out the 9, leaving me with 1 minus 1/9 x, and you can verify that if we multiply the 9 through, we will get 9 minus x. And then I take the negative 3 over 9, and that becomes my a, because having a 9 in the denominator of this fraction is the same as having a 1 over 9 in the numerator. So my a is negative 3/9. My r then is 1/9 x. I can then, and then I do the same thing down here. The 7 plus x, all I have to do is factor out the 7. But be careful because, remember, this term right here is a minus. That term is a minus. I have a plus here. So we're factoring out a negative. So it's 1 minus a negative 1/7 x. Again, you can verify by multiplying these that you get that. And doing the same thing I did up above, 2/7 becomes my a, and then negative 1/7 x becomes r. The next step is to put these in the form of a power series. Now that we know what a is and r is for each of these, f and g, we put them into the form of a power series. And so that's what I'm doing down here. So I'm just trying to figure out how I did this. Okay, so this one was pretty straightforward, I guess. Yes. So we have the summation from n equals 0 of my negative 3/9. That comes down here. And then the 1/9 x, or x over 9, to the nth power. And so that is my power series in geometric form. That's a geometric power series. G of x, do the same thing. It just takes an extra step. And so we go through and we plug in the 2/7, plugging in the negative 1/7 x as x over 7. And I want to factor out this negative. Okay, I don't want a negative in there. So I factor out a negative 1 to the n. And you can verify that this is going to be the same as this right here. So I factored out that negative. So we have an alternating series for g of x. So remember what we're doing here. Let's not lose track of what we're doing. Let's go back to the original problem. We're using partial fractions to find the power series for this x plus 39 over x minus 9x plus 7, which we have rewritten now as this. So we now have a power series for this. We now have a power series for this. We need to subtract the two of them. So we need to subtract our power series. Finally, we're getting to the part where we're combining the power series. And so that's what we are doing in this last step. So here we have f minus g would be this power series minus g. And so instead of doing this term by term, the answer that they are looking for this particular problem is to combine it as a power series. And this, again, is a little bit of tricky algebraic maneuvering. Notice that there is a 9 in the denominator of both of these. So you can rewrite all of this with a 9 in the denominator. And so so we have x over 9 to the n is really x to the n over, 9 to the n. That's not coming out very well. And so if you have 9 to the n in the denominator here, and 9 to the 1 in the denominator here, and you're multiplying, you add the exponents, which is where the 9 to the n plus 1 comes from. And so we've done things similar to this in the previous section. But once again, what I'm doing is this is 9 to the first power. This is 9 to the n power. We're multiplying the denominators, so it would be adding the exponents 9 to the n plus 1. And in the numerator here, it's just 1 to the n, or 1. So 1 times negative 3 is negative 3, and times x to the n. And then we're doing the same thing over here. We have 7s in the denominator, so we get a 7 to the n plus 1. And then we have the x to the n comes out here. And then we have a 2 left in the denominator. And negative 1 to the n changes negative 1 to the n plus 1. That's just to get this sign correct. Once we change this once we've kind of changed this around a little bit. Okay, now, then all we're doing going down to this last part here is factoring out the x sub n and then just rewriting these two terms as a sum. And so we have the first term and the second term. It's a rather complicated little answer, but the idea behind these problems is that power series can be combined. Plus, this is a good problem because it's a practice in partial fraction decomposition, which we've learned to do as a technique of integration. It's a good way to reinforce how to write a power series as a function, or a function as a power series. Next example. This one's a little bit easier. Probably should have done this one first. Express the series as a rational function. So 1 over x to the 2n can be easily rewritten as 1 over x squared to the n. So you can verify that 1 to the n is just going to be 1 in the numerator, and x squared to the n in the denominator would be x to the 2n. Well, once we have that, we see that a is equal to 1, and r is 1 over x squared. So putting that in the form of a power series, we have 1 over x squared to the n. That's that's just rewriting the power series. We haven't actually done anything yet. We haven't written it as a rational function. We're just rewriting the original power series so that it looks more like a geometric. Now we can write the sum. Well, a is 1, and then 1 minus r, and then we want to simplify that. And we can simplify that by multiplying the numerator and the denominator by x squared to end up with this, and voila. That is a rational function. And so that would be our answer to this particular problem. And let's see the next problem. Now this particular problem, just a word of caution. If you were to see this on an exam, I would be asking the question a little bit differently. And the reason is that the answer to this problem, calculate the present value of annuity, is very simple. You just take the 12,000, you take this number, and you divide it by that. And so if you were to take a finance class, like business finance, this would be the formula for figuring out the present value of a perpetuity. A perpetuity is an income that is generated every year annually, or whatever the time period is, to infinity. What we want to do is derive this formula. So in a question on an exam, I might ask you to derive the perpetuity formula using series. So as you can see, the final answer way down at the bottom is simply present value is equal to A over R. And so as I said, it's just 12,000 divided by 0.06. So the answer is 200,000. That's a very easy calculation. What we want to do in a calculus class is we want to figure out where that formula comes from. One of the interesting things about finance, if you've ever taken a finance course and you've dealt with annuity formulas and savings formulas and interest formulas, they can all be derived through the use of series. In fact, that's where they do come from, actually. So the theoretical development for this is we have to have a starting point. And so the starting point that I'm going to use here is this formula. Okay? The present value, P, is equal to the amount. I'm going to call A the amount, which in this case is the 12,000, the amount of the annuity, divided by 1 plus R to the N. R is the rate, which in this case is 0.06, and N would be the number of compounding periods, and since we're talking about annual, it would be the number of years. Now, you could actually go through and derive this formula through a little bit of intuition and just thinking about the problem, but I'm just going to save you a little bit of time and saying this is the starting point. This is the formula that we're going to use to work with here. So the present value is equal to the amount that we're dealing with divided by 1 plus R to the N, where N will take on the values of 0, 1, 2, 3, 4, etc., etc., etc. And so that's what we're getting at down here. Using this little formula, I can say, okay, right now at year 0, which is now, what is this $12,000 worth? Well, it's equal to A divided by 1 plus R to the 0. Well, we know anything to the 0 power in the denominator is 1, so we have A divided by 1, or just A, and that makes sense. That right now, our amount, which is 12,000, is just going to be equal to the amount, A. In year 1, this would be at the end of 1 year, we would have A divided by 1 plus R to the 1. That's what the value, that's what the present value of that would be equal to. It would be equal to the sum of these two terms. So we're looking at partial sums here. At the end of year 2, the value of this annuity is going to be equal to the third partial sum, S sub 3, taking all three of these and adding them together. At the end of year 4, we would be looking at the fourth partial sum, the fifth partial sum, all the way up to the nth partial sum. So now let's write that as a geometric series. And so the geometric series is just simply going to be A over 1 plus R to the N from N equals 0 to infinity. And so rewriting this so that it looks a little more geometric, we can write it like that. We can factor out the A, the amount, which becomes our A sub 1 is equal to A. And then our R becomes 1 over 1 plus R. Right? So it's this whole thing is our R value raised to the N power. Now, so what we're doing here now is factoring out a 1 plus R factor from here. So we're starting with 1 over 1 plus R to the N, and so this would be to the 1. And we're factoring that out, and so you can see that then we then subtract 1 from the power here. And you can verify that if you multiply these two terms together and you add the exponents, you will get this term up here. And the reason that we're doing this is we're going to multiply that by the A to give me this new A sub 1 value. So we have our A sub 1 value, and we have our 1 over R is still our radius. Our R value. Okay, now we can put this together in the formula for the sum of a geometric series. Again, we're dealing with a geometric series here. So in the numerator, we have our A value, A sub 1. In the denominator, we have 1 minus R. And so that's a little complicated. So to get rid of the complex fraction, we're going to multiply by 1 plus R over 1 plus R. And we do that, we end up with this. Canceling out the 1's, we end up with our final formula, which is A over R. Which is the A over R. And so that's how we derive this particular formula. It's a very, very simple formula derived through the complicated process of combining power series and working with power series. So, as I said at the beginning of this problem, many problems are actually derived from series, a lot of finance formulas. All right, one more problem here. I think. Yep. So the last problem, we want to multiply two power series. So we're multiplying f times g. So the first step is to expand each power series. I didn't write it over here, but this is f, this is g. And so I expanded out the power series. I expanded this out. And then we need to multiply those, term by term. So we take f, this is f, and we're multiplying it by g. Everything with series is looking for patterns. So we want to do this very methodical. So what I'm doing is I take g, all right, and we're using the distributive property here. I'm multiplying g by 2, the first term here. Multiply every term in g by 2, and I get this. So 2 times 0 is 0. 2 times x is 2x. 2 times 2x squared is 4x squared. 2 times 3x cubed is 6x cubed. Then, let's go to another color. I take the 2x and I multiply it by every term. 2x times 0 is 0. 2x times x is 2x squared. 2x times 2x squared is 4x cubed. 2x times 3x cubed is 6x to the 4th. And then, et cetera, et cetera. I do it with the 2x squared, and I get these terms. I do it with the 2x cubed. I get these terms. And notice that I'm also lining up similar terms. Okay? I'm lining up the x's, the x squareds, the x cubes, et cetera, trying to do this as methodically as I can. And now let's add up the similar terms. So when I add up the similar terms here, I get this. So we get 0, 2x plus 0, 4x squared plus 2x squared plus 0, 6x cubed, 4x cubed, 2x cubed plus 0, et cetera. We can almost predict what all of the future terms are going to be, even though we don't have them all. We can already see a pattern developing here. So again, I label my n equals 0, n equals 1, n equals 2, n equals 3. We look for the pattern. So clearly we have an x to the n. The part that, again, is tricky, that you just have to kind of work with, is you have to see what is the relation of this number to my n number, this number to my n number, this number to my n number. And so sometimes you need to play around with that a little bit, but it ends up being n times n plus 1. Just kind of keep that in your bag of tricks. Sometimes it's your value of n times some other value of n. So you can check this out. When n is 1, we have 1 times 1 plus 1 is 2. 1 times 2 is 2 times x to the first. So it works out. If you do this for each term here, you will get the appropriate term. And so that is the product. This power series here is the product of our two original power series that we were given up here. All right, in the next video, we're going to be taking a look at getting into some calculus, differentiating and integrating power series.